Let's try to solve this example differential equation, and the solution will be a power series. Another thing I want to show you is that this is a case where you don't have an initial condition. If you have y of 0 and y prime of 0 given, then those values will be the values for a0 and a1. So it's relatively easier, but I want to show you something that does not have the initial a0 and a1. Okay, so let's get to work. First, what you want to do is you want to start with this power series. You have y as a0 plus a1x and a2x squared and so on and so on. That can be written this way. And what's really important that you should be able to go back and forth between this sigma notation and the actual form. So for example, this actually means when n is equal to 0, this is a sub 0 x to the 0th power plus a1 x to the first power, a2 x to the second power, and so on, right? And of course, if you differentiate this, these numbers on top will come down. And by the way, the x to the 0th power is just 1, so this is a constant term which will go away. That means that the derivative will start from here. So let me show you what the derivative looks like. If you differentiate the left side, if you differentiate this, then this is a constant term, so it's going to go away, and x to the first power will just become 1, and then 2 will come down and you're going to get first power, and then the next one here would be a3x cubed, right? So if that one's differentiated, you're going to get 3a3x squared, and so on, right? So the formula you end up getting is here, and you know that because if x to the n is differentiated, n will come down, and then you're going to get n x to the n minus 1. Moreover, as you can see here, n should start from 1 because the very first term is a1, not a0, right? And then differentiating once more will create another n minus 1 coming down, and this will become n minus 2, and this time n will start from 2. Okay, so once you're convinced that these are the power series first derivative and the second derivative, then the next thing you have to do is, anytime you have more than one term inside the parenthesis like this, before you try to do the power series solution, you must break this up into two parts, just like that. Okay, so 3x times y prime, and then 2 times y prime, just like that, right? And then we can plug in this one into y prime. We can plug in y double prime as this one, which will result in the following series. Okay, now starting from here, I actually have to type a lot, so bear with me here. So what I want to do is I want to move this 3x inside, and then say, oh, x times x to the n minus 1, that's just x to the nth power, isn't it? Right? So yeah. X times x to the n minus 1 is same as x to the first power times x to the n minus 1, so that the powers, they add up, so you end up with x to the nth power, just like that. So that's why I wrote down x to the nth power. 2 can also be moved inside, and then 4 can also move inside, so I'm going to move all these inside. And now comes the shifting. Shifting means when you have a bunch of summations, in order to use some mathematical theorem called identity theorem, you have to organize everything in terms of the powers of n. So you really need to match the powers of n. Seeing that x to the n is here and there, we can, if we want to make everything as x to the n, this term and this term, these two summations should be shifted. Okay, and let me try to explain what shifting is carefully. So what you do is, I want this n to be n minus 2 to be n. How can you make that work? Well, you replace n by n plus 2. Okay, and you can't just do that to only this one. What you need to do is, you can, if you want to replace n by n plus some integer or n minus some integer, anytime you do that, you have to replace every n that you see in this sigma. Okay, and especially when n was there and it's a multiplication, make sure you introduce this parenthesis, because this entire thing, it was n before and it has to be multiplied. If you don't have the parenthesis, then only 2 gets multiplied, and that's not the true representation of what happened before. And here, lastly, this one would be n plus 2. So I changed every n to be n plus 2, and we're almost there. Now we have to simplify. N plus 2 equals to 2 is same thing as n equals to 0, right? So I make that as n equals to 0. N plus 2 minus 1 would be just n plus 1. N plus 2 minus 2 would be just n. And I claim that this summation is exactly same as this summation. And if you don't see it, I really want you to stop the video and check it by writing all the terms that's produced by this. So the very first term produced by this is when n is 2, it's 2 times 2 minus 1, which is 1. So it's 2 times 1 times a2. X to the 2 minus 2 is 0, so x to the 0th power is just 1. So the very first term this will produce is 2 times 1 times a2. Whereas here, if you have n equals to 0, this is 2 times 1 times a2 x to the 0th power. So it's exactly same as the previous one, which is 2a2. So they both produce 2a2 as the very first term, and then you can proceed to check what happens when n is 3 here and when n is 1 here. You see that they produce exactly the same term. So this is just renamed in a different way. It looks different, but they're exactly the same terms. And the reason you want to do this shifting is because you want x to the n to be same as the other ones. Okay, so let's proceed. This one, there's no problem. It's already x to the n. This one, we need to shift, right? So here, I guess this one we need to put as n plus 1, so that n plus 1 minus 1 is 0. And it's just n. So plus 1. Here it's multiplied, so you want to write it as n plus 1. And even this one as n plus 1. And then you simplify. N plus 1 equals to 1, simplifies to 0. And then this one just simplifies to n. And then plus this thing equals to 0. Okay. Okay. All right, so now that we have everything in the form of x to the n, let's just check one more time we have it right. So these are untouched. This one, you replace n by n plus 1. Looks right. Okay. So now we can take this and start solving. So let's delete other ones to give some room. When you deal with this, notice that these sigmas are like factories, but it's a factory where they make individual terms. Mathematical terms are produced in each of these factories. And when n is 0, let's say that's like the noon time, the first sigma factory and third and the fourth sigma factory, these are working. They are producing something. On the other hand, this second sigma factory, the workers don't start doing anything until 1 o'clock. But at 1 o'clock and afterwards, all of these factories are working. They're producing something. So what you want to do is you want to rewrite this summation with a single clock. So what happens when n is equal to 0? Well, when n is equal to 0, this will be 2 times 1 times a2, x to the 0th power, so you're going to get 2a2 from the very first sigma. This one will not produce anything, so we skip. And then the next one, this one will produce, well, let's see, if n is 0, it's 2 times 1 times a1, x to the 0th power, so it's just going to be 2a1. And then the last one will be plus 4a0. And these are the terms produced by the first, third, and fourth sigma factories. But then starting from 1 o'clock, all of these produce something. And the nice thing is, since they're all working, you can just use one single sigma to keep track of all the terms. So so what you want to do is you can put this, you can take this thing, put it in here, take this one, put it in here, take this one, put it in here. Okay, maybe let's do it like this, okay? And this entire thing, all of these terms are produced, so I'm just using a single clock to keep track of the time. So I'm using an analogy, okay? Hopefully that makes more sense, okay? All right, and that's equal to 0. And once again, I challenge you to verify that indeed the terms produced by this new format is exactly same as the terms produced by these. So if you actually wrote down all the terms that are produced by each one of them and compared to here, they're still the same. And one more thing, because all of these x to the n's are the same, I can factor them out. So I can delete them inside and just bring it outside right here. Okay. So now you have this plus this x to the n equals to 0, and that allows us to now apply something called the identity theorem, which says that if you have a power series organized in terms of powers of x, so even this first one, that's like times x to the 0th power, right? So all of them look like something times x to the 0th power, and then x to the first power, and second power, and third power. When you get the power series to look like that, and if that's equal to 0, the identity theorem of mathematics is some theorem that appears in complex analysis, so it's outside the scope of differential equations class. But if you trust the mathematicians, you can say that this has to equal to 0. And all of these individual coefficients must be 0. Has to be 0. Okay, so now what? The very first one, or the first few, they don't follow a pattern because some of the factories are not yet working. So this is a case where it doesn't follow the pattern. But after 1 o'clock or afterwards, n equals to 1 and afterwards, this is always true. So it follows a pattern, right? The ones that do not follow the pattern, you have to solve it individually. And when you solve it, you want to solve for the higher order term. So a2 here, 2 is the highest, so you want to solve for a2. Let's solve it and think about what it means. So 2a2 is equal to negative 2a1 minus 4a0, so that if you solve this by dividing by 2, you have that a2 equals to negative a1 minus 2a0. Okay. Now, what does this mean? Well, see, our differential equation doesn't have an initial condition. If the initial conditions were given, those will be values of a0 and a1. So you can think of a0 and a1 to be variables that are yet to be determined if there were initial values. Or another way, you can say that since second order differential equations have two free parameters, these will be the two free parameters, okay, which can always be changed to match with any initial value problem given, okay? So it's a good thing. So we can treat a0 and a1 as some known values, or some known values in the future if the initial value problem is given. And therefore, it makes sense to solve a2 as expressed as a1 and a0. And in fact, once you realize that, you see that the point is to solve all of the following formulas as a1 and a0. So you want to express a3 as a1 and a0, a4 as a1 and a0, and so on and so on. Okay, so that's what we get. Now let's work on the following thing. This one, again, n plus 2 is the highest index. It's higher than an and an, right? So that's what it is. So what we want to do is we want to, we want to move all of these terms to the other side. So let's see. I'm going to put an equal sign and put minus here, and minus here, and then minus here. Okay, so all of these terms went to the other side, so they all get minus signs. But then since this one has an and this one also has an, you want to combine them and rewrite them as negative 3n plus 4 and delete this. Okay. All right, so what was there before? I combined the two by factoring the an out. So we have this, and then you divide by an plus 2, and then an plus 2 will now be this thing on the right side, and divided by this one, because I'm dividing this to the right side. So each one of these will be divided by n plus 2 times n plus 1. So this one also I have to divide by just like that. Okay, and this one is true. Oh, by the way, I guess it's better to move this one afterwards here, because then this is highest, the next highest, and the next highest. This seems better. Okay. All right. So this is what's called the recurrence relation, because this is a pattern that's always true for n1 or greater. Remember, this here is true for n1 or greater, and setting this equal to 0 ended with this one. So this is what we call the recurrence relation, and for any recurrence relation, you should always write down the values of n which it's valid. Okay, without this, if the question is find the recurrence relation and you don't have this, then you will have points taken off. Okay, so that's the recurrence relation, and by making use of this recurrence relation, we can keep solving. Okay, so let's make some room for the other parts. So I'm going to delete these. Okay, delete these as well. Okay, so we're very close to solving it. So we have, therefore, when n is 1, we have a3, right? So let's see what happens when n is 1. So we have a3 equals to negative 2 times, if a is 1, 1 plus 1 is 2, 2 times 2 is 4. So you get 4 divided by, let's see, 3 times 2, a2, right? And then minus, when n is 1, 3 times 1 plus 4, that's 7, right? 7 divided by, again, it'll be 3 times 2, a1. But this is, I don't know why I have a parenthesis here. Let's write it without a parenthesis. It's not important. Okay, so here, this is not done yet because a2 is not your goal. You want to ultimately express everything in terms of a1 and a2, and a1 and a0. So this a2 has to be expressed as a1 and a0, which we already know. So what we want to do is we want to replace this one, this a2, by negative a1 minus a2 a0. So let's do that. So that's equal to, let's see, 4 over 2 is just 2 over 3. So it's negative 2/3 times this thing here. And then the other one, you keep it. And then if I simplify further, we get positive 2/3 a1, and then plus positive, well, negative 2/3 times negative 2 would be positive 4/3 a0. And by the way, this is, let's just rewrite this as 6. And so this would be 4 over 6 minus 7 over 6. So that's going to be equal to negative, okay, 4 minus 7, that's negative 3. Okay, so negative 3 over 6 a1 plus 4/3 a0. And because 3 over 6 is 1/2, let's just rewrite this as 1/2. So that's a3, right? So we've expressed a3 as this. Now, if you can find the pattern, that's even better. That means you can actually solve for all an, and you can write down the solution explicitly in full. But in most cases, what happens is it's extremely hard to find the pattern, so you just have a3 as something like this, and then a4 is something with a0 and a1. And if you have until a4, that's probably what people want, because a lot of times when I put this as a question on the exam, I will say, find the first 5 non-zero terms of the power series solutions of this. And because you have a0, a1, a2, a3, a4, giving you the 5 terms, I would terminate at a4. So let's just do one more here. So a4 would be, let's see, a4 would be, that's when n is 2, so I'm going to use this one, but with n equals to 2. If you have 2 times, oh, there's something I forgot. See, n plus 1 and n plus 1 cancels, right? That would have made my life a lot easier. Okay, so that's a lot easier, right? So n is 2, then it's negative 2 over 4 a3 minus, when n is 2, 2 times 3 is 6, 6 plus 4 is 10, so it's 10 over 4 times 3 a2. And again, you have to rewrite a3 and a2 by the ones that you found previously. But let's first simplify this. So that's like negative 1/2 a3, and then minus 5 over 6 a2, and then now you replace a3 and a2 by the values you found. So where is it? Here, negative a1, negative 2a0. So replace it. And then a3 can be replaced by this one, so let's replace it. Okay. And then that gives you positive 1/4 a1. And then 4 divided by 2 is just 2, so it's negative 2/3 a0. Then minus times minus is positive, so it's plus 5 over 6 a1. And then negative 2 and 6 cancel, so it's 5 over 3, so it's plus 5 over 3 a0. And then the common denominator between 1/4 and 5/6 is 24, so we can further simplify this as, well, you know what, let's make this, let's delete some terms. So since I've already used up this one, so I'm just going to delete that. Let's delete this one. Okay, and then, all right, now we have room to continue on with this calculation. So this calculation will simplify as, let's see, this will be 6 over 24. 1/4 is 6 over 24, whereas if you multiply 4 top and bottom, that will be 20. Oh, actually, 12 is the least common denominator, so let's change it. So multiply 3 top and bottom, so it will be 3 over 12. And then multiply 2 top and bottom, that will be 10 over 12. Okay. So now we can combine them easily. So let's see, 3 plus 10 is 13, so it's 13 a1, 13 over 12 a1. And then furthermore, so that's gone. Furthermore, 5 plus negative 2 is 3, but 3 over 3 is 1, so you just get 1 a0. So that's your a0. Okay, so that's your a4. Okay, so we've done a lot of work, and now let's try to actually write down the solution using all this. So here's how you say it. Where did we start with? We had this this is our definition, right? Or this was our definition, right? So that was our y. So this is y. And because I know a2, well, let's just put a4 x to the 4th. That's 5 non-zero terms. So I know that a0 is just a0. We'll rewrite x0 as just 1. a1 is a1. I'll just rewrite this as x. And then a2 is now replaced by this one, so I'm going to put parenthesis. And then a3 is written like this one. And a4 is this one. So I rewrite it. And this is 5 non-zero terms. Now there's one last thing I want to show you. See, a lot of times people want to write it so that it's a0 times something plus a1 times something, just like if you have a second order constant coefficient, the solutions are like c1 times a function plus c2 times another function, so that c1 and c2 are the free parameters. So often they ask you to write your solution in that form because that way it can identify the pattern better if there's a pattern. So what I want to do is I want to factor an a0 out and just write down all the terms that has an a0. So a0 times 1. X doesn't have any a0, so it's just nothing for x, but then for x squared, that's minus 2. That's minus 2a0 x squared, right? Oh, a0 is already there, so I don't need to write that. Right? If I take this much and factor the a0 out, you're going to end up with negative 2x squared, right? And then the next one for x cubed, you have, if you take the a0 out, you have 4/3 x cubed. So it's 4/3 x cubed. And then this one is just a0 x to the 4th, so it's x to the 4th plus dot dot dot. So that's your first function. And sometimes you end up getting a pattern. I don't see any pattern here, so I don't know. But sometimes you do get a pattern easily this way. Okay, and then for a1, a1 is not in the constant term, but it's a1 times x. So if I factor an a1 out, then you get x. Here you get negative x squared. And then minus 1/2 x cubed. And this one is 13/12 a1 x to the 4th, so it's plus 13/12 x to the 4th, and then parenthesis. Okay, so that way, oh, plus many other terms. It's infinite series, so you always need this. Okay, so you have these two mysterious functions. It will be some special functions. I have no idea what these are, but you're going to have those, and it's a0 times something plus a1 times another one. So a0 and a1 are the two free parameters. And that's it.